Okay, too loud. Okay, we're going to start today by just go through what we're going to cover for this course and what are our targets, at least every week. So there's basically two main parts that we're going to discuss. I think maybe 1/3 of the semester we're going to focus on the introduction of semiconductor devices. First of all, before we start understanding how these devices operates, its basic mechanism, how do you analyze or model them, we're going to go through some, very quickly go through, I think, probably just a week or so. We'll go through semiconductor physics, and then just give you a sense as to how does these charge carriers generated and how does one control it through semiconductor technology to understand how do you actually make these type of structures. How do you make it function? Not necessarily how do you manufacture these devices, but just to give you a sense as to why do you, how does one use semiconductor, and you do doping, how do you control the carrier concentration, and what are the transport mechanisms? We're going to cover that just hopefully today. And then we're going to enter some discussion as to why these transistors or why these devices function as it is. So we're going to introduce these device characteristics when you apply current voltage relationship. So mostly is current voltage. When I apply a certain voltage, what is the corresponding current, and how does that changes under different situations, different biasing conditions? And we're going to talk about models, of course. Model is one of the linkage between a device. Once we have a device, we build a model, mostly a current equation. So these are current equations, mostly current equations. So we build, these are typically called first order model. We get the gist of what is the most fundamental or the most dominating mechanism that controls the transistors. Of course, there's more complicated model once you go to more advanced designs. But we're going to just go to the fundamental first order model. Once you have the first order model, and you get a sense as to the linkage between the equations and the current, and the actual physical mechanism, then we can actually do modification to have more refined models. But in this class, we're going to just fall back to the first order models. And then once you have these diodes, these are the devices we basically use in these type of circuits are included here. These are diodes, transistors, bipolars, and MOSFETs. So we'll cover them in different chapters. We're going to focus on the operation mechanism and why do we have, for example, a p-n junction. We're probably going to touch on that just starting part next week. And then you get a sense as to why do you get, for example, for a diode, you get a nonlinear IV characteristic. Why do you have these nonlinear characteristic? Why does it forward bias, you allow current to flow, reverse bias is not flowing? The reason why the linkage between its physical structures and semiconductor designs. And then once you have these devices, adding the passive components we discussed, resistors, inductors, and capacitors, then you got yourself circuits. So then we can start building circuits afterwards. Once we establish our fundamentals of building blocks, you understand how these building blocks behaves, then you can start building circuits, okay? Good? So it's probably, I think, on the first half of maybe 1/3 of the classes, we're going to focus on part one, which is the device and characteristic and how does one model it. That's the key thing. And the second part, we're going to enter the analysis, circuit analysis part. So first of all, we're going to tell you how do you analyze a circuit. How does you, as I said to most of previous classes or when I introduced this study is that I think microelectronics it's not a very easy course to learn because you need to master the ability of zoom in and out. Or when I mean zooming in is that when I'm introducing semiconductor devices, I'm talking about electrons, carriers, how do they move, drift or diffusion. You look at the tiny movements, small movements of carrier, you zoom in, you look at a microscopic view of the carriers. But then, if you want to analyze circuits, it's a larger view, so you have to zoom out. So there's a zoom in and zoom out. You ignore stuff when you zoom out. So how do you make approximation that make yourself, when you handle large systems, how do you handle, and there's this type of zoom in and out actually exists in every analysis or every disciplines. So the way to, when do you need to zoom in? Where there's a problem, you zoom in. When there's a leakage in your building, you zoom in and see what happened with the concrete or something. But when you're looking at it like urban structure, you zoom out and look at building as each blocks, okay? So these are the things that we're gonna learn as to how do you zoom in and out. So there's different type of approximation level allow you to see the larger view or smaller view. So I'm going to tell you how to analyze it. They're basically DC-AC analysis, and we're going to set something called the operating point because in most of these studies of analog circuits, the signals are carried in small signal, meaning that the signals, the oscillating signal, which will typically stand in a particular point. So we're going to talk about how does one do an operating point analysis. Where do you want to stand or position, called the operating point. So if you ever do SPICE simulation, if you want to do small signal analysis, you start with OP, operating point. You find your standing point, and then you at this particular standing point, you do linear projection, and we do this small signal analysis. It's called small signal. Approximation. It's approximation because you want to zoom out. You zoom out and you're looking at the larger picture as the projected behavior. We're going to talk about that later, but that's how you're going to use for circuit analysis. And then, of course, when you go through examples, we're going to, as I said in our previous class, you start with looking at typical designs. What are the typical things people have been doing? You look at typical, very easy structures. We look at single-stage amplifiers. These are the type of single-stage amplifier in bipolar circuits. And then we're going to also look at the counterpart, which is the MOSFET, but it's basically operating in a similar ways. And then once you have this single-story layout you're familiar with these single-story layouts, then the next thing is that you look for more complicated structures, something like Cascade. You're building the second floor now. So if you want to build a second floor, it's like a Cascade structures. Or if you want to do biasing circuit, that's called a Cranio. So these are the two very important modules in analog circuits and amplifier circuit design. So we're going to talk about how does one approach this type of structures and what is the benefit and drawbacks of using this type of structures. And then we're going to talk about something called a differential pair. If you, after the class, you go back to the cathedral, the 741 operation amplifier, there's always differential pair in the system. The reason why it has differential pair, we're going to explain the reason of operating something. Differential pair is a particular structure, but differential operation. The concept of doing differential operation, we're going to spend some time talking about it. Why and why. Understanding why is very important, and see if by doing so you can actually improve the signal. This is mostly for noise reduction. So how do you suppress noise through a differential operation? It's like, we're going to talk about that later. And then finally, we're going to talk about response time, speed. So let's analyze frequency response in our I guess the first section of circuit analysis, we ignore the high frequency, assuming all the devices are working low frequency in a very low, slow pace. So you don't actually care about your baggages. So when you're moving at a faster speed, when you look at, if you're operating in different frequency, what is the response of your circuits? That's called the frequency response analysis. And how does one analyze that? That include also the models of transistors has to be more refined, because beforehand you don't actually see these baggages, but if you're running fast, you'll see that whether you should lose a few pounds. So these are the things that we're going to talk about, okay? Any questions? I'm not talking too fast, right? It's good. 还可以吧? Is the speed okay? Okay. So if I'm talking too fast, just let me know. I often move too fast in most cases. Okay. So before we actually start on chapter 2, which is semiconductor physics and p-n junctions, I would like to just briefly align with you. Assume most of you taken courses I think it's, what is the number? 2210? 电路学. Most of you have to circuit analysis. For those of you who have taken circuit analysis, please raise your hands. No? Yeah, most of you, right? So I don't need to spend more time on it. I'm just going to review just to align that what are the things we're going to use in this class, and I'm assuming that you know all that. So first of all, I'm assuming everyone knows KCL. It's called the Kirchhoff current law. So what it does is that it's assuming that in a node, if you have multiple current coming in, I1, I2, I3, I4. So if all the currents coming into one node, what happens is that all the current added up to a collected node will be what? The sum of all current into a collected node is 0, correct? That's KCL. So through this, we can actually expect that if you know 3 of them, you should know the 4th, right? So I'm not going to go through any example. I'm just going to move on quickly. So for other part is, of course, KVL is a conservation of potential. So let's say if I have a loop, I have multiple devices connecting in a loop. So what happened is that, just make sure that I'm applying it correctly. So in a loop, then the voltage is supposed to add up, and then also conservation of your potential in a loop. So you should be able to, once you know 3 of them, you should know the 4th, right? So these are the basics one should know. And aside from using KCL and KVL, the other thing we use is a lot is called the equivalent circuits. I assume that everyone knows that for capacitance, it's impedance. For capacitance is 1 over j omega c. This is because your current is based on the your voltage on capacitor. I should say, let me write it down. In time mode, this is a frequency domain, but in charging current depends on di voltage change. That is why its impedance is actually 1 over j omega c, right? For passive component, the other passive component is impedance is inductor is j omega L. This is because the voltage across, let's see, just label it correctly. The voltage across inductor is induced by current changes. Right? And then that's why you get these impedance. So once you have the network of passive and active components, we should be all of the capacitive components combined, for example. So when you talk about equivalent circuit when in impedance, equivalent impedance, therefore you need to know that all the passive components has a impedance that can be reflected depending on frequency, or for resistors, of course, is equals to R. Okay, so I should put it here. So 3 passive components, just to be aligned. IR, VR. So this is its impedance. Of course, it's just a independent of frequency. Okay, once we get that, we could start to build we're going to introduce something called the Thevenin. I believe you have learned this, but just to review, Thevenin and Norton equivalent circuits. The reason we do this is to make sure that you can simplify something with a black box just to understand its voltage and current relationship. So for example, if I have a circuit with an independent current source, independent voltage source, sorry. So this is an independent voltage source. I have some independent current source. And then I might have all these passive components, inductors, capacitors, and resistors. So what we want to do is that if you're connecting these modules with other circuits, what's typically done is that I can wrap this thing, shield it with a black box, and then say that its behavior is the same as either a Thevenin, V Thevenin. You lump everything in here, and then this is Z Thevenin with this model, so that it actually has the same behavior at the port, at this. If you're looking in, because I'm wrapping it up, I'm only looking in here. I'm looking at the corresponding voltage and current relationship. As long as it's identical to that, that's called the equivalence. So this is called the Thevenin. And you can also do the Norton. So Norton is using independent current source. It's using a current source instead, not necessarily independent. I'm sorry, it's not a resistor. Okay, so that's called a Z. And then this is I Norton. That's called the Norton equivalent. If you want to represent the behavior, the current voltage relationship with a current source, then we use Norton. If you want to represent it as a voltage source, then you use Thevenin equivalent. So how do you determine this? How does one, if I give you this circuit, how do you get these two parameters? We need to find this and this. Okay? So if I want to measure a voltage of a circuit, what do I do? Typically, if you have a circuit, you want to measure the voltage across. What do you do? What do you use for voltage measurement? What is it? 伏特计, correct. is a voltmeter. You use a voltmeter, and the voltmeter, if you're looking at a circuit, the voltmeter is an open circuit, right? It has the highest and close to infinite impedance. So what we do is that if you want to measure, so let's think about a Thevenin equivalent. So how does one determine how to determine V Thevenin and Z Thevenin? So I'm just gonna, so first of all, you measure it with a voltmeter. So we measured the voltage across two terminals measured by a voltmeter. So because voltmeter has close to infinite impedance, that means that you opened circuit, opened output. I should say, I made this current or so the output terminal is open. Simply means that there's no current on the output terminal. So I, meaning that I'm setting, let's say this is IO, VO. So if I'm open this two connection, meaning that IO is zero. Okay? So let's give this is more, let's just give an example. Let me draw an example. We're setting this to 0. This is open. And let's say if this is 4K ohm, 1K ohm, just give a simple example for simple calculation. So what happens is that if I'm open, this is 0, there's no current, this is open. So you don't see the spread, there's only one current flow. Therefore, we know that the measure, in this case, is V Thevenin equals to 8 volt, right? So 1 plus 4 times 10. That's 8 volt. So we know that for this, if you want to transform it into Thevenin equivalent, the current, the voltage is 8 volt. And it's, so the second part is, of course, how do you find Z Thevenin? To find Z Thevenin, you simply set all, let me highlight it, independent sources to 0. So this is an independent voltage source. Independent, I want to emphasize, this is only work for independent. If it's a dependent source, meaning that voltage control current source or current control current source, that's called dependent current source. This is independent because it does not depend on any component parameters inside the circuit. So you set independent current sources to 0, then the circuit becomes this. 1K, 4K. Of course, if it's much more complicated, and how does one determine the resistance or impedance? You give we give it a test curve. Sometimes, so how does one measure the impedance? You give we call it test voltage, and look at its response, test current. And so Z Thevenin will then be Vx Ix. And it will simply be 4K in parallel with 1K. Okay? That will be 0.8. Good? So you can also do the same exercise for Norton, because for Norton we're measuring current. Therefore, you use an ammeter. So let me use up this page. So if I want to use a Norton equivalent, how to determine I nor and Z nor. So we measure, first of all, instead of using a voltmeter because you want to assess the current components, so you measure by ammeter. So we know that ammeter has a resistance, internal resistance of what? 安培计的电阻多少？我会问就是一定是 either 是 infinite for voltmeter, so ammeter is 0. Yes. So internal resistance of ammeter is close to 0, so you short. We short output. Simply means VO equals to 0. Okay, so for your equivalent circuit, we're going to short it so that the equivalent circuit will look something like this. I have 1K and then 4K ohm, and then I'm going to short the output and measure. This will be my I nor. Or we can measure with an ammeter if you want to just put it here. So it's a short. So basically I nor is how much? Is 10. This is 10 volt. 1K. So it's 10. Okay? That should be quite straightforward. And in this circuit, your Z7, Z nor actually is the same because I only have independent sources. So I'm setting out I nor is actually the same as Z7. Okay? So this is identical. So then your Norton equivalent, I didn't actually draw it. So from that circuit, we can actually generate our two equivalent circuits. They're equivalent, therefore, three of them are equivalent. It doesn't matter. You can substitute them equally into the system and it should give you consistent results. That is to say, circuit 1, which is the original circuit, 1K ohm, 4K ohm, 10 volt. It's equivalent to the Thevenin equivalent. This is 8 volt, 0.8 volt. And it is also equivalent to 10 milliamp. Sorry, I made a mistake. 0.8 volt. They are all identical. They are equivalent. Not identical, I'm saying. They are equivalent. So you can substitute the circuit. You can use this, and that. And if you connect it to other, to do circuit analysis, it should give you consistent results. And the reason why you're picking one over the other, of course, we're picking these is to simplify. If you have a complicated network, you don't actually care what's happening internally, then you can simplify simply by this to have a simple interface with other circuits, other building blocks. Okay? Good? lastly, before we actually move on to chapter 2, I want to, let me get rid of this then. I assume everyone knows Ohm's law. So we're going to look at Ohm's law. We have already briefly talked about Ohm's law in a different version if you're looking at it as a sheet resistance. So let me discuss that in how does one view resistivity or Ohm's law. So let's say if I have a resistor, a large if I'm looking at a resistor in a material, so let me first define a resistor by a block of material. So we talked about that briefly last time, but I'd like to review that and then we can look at it in 3 different perspectives. Okay, so let's say if I have a block of material with, this is its thickness. Let's define it well. Thickness, and then I have a width. And then finally I have 3 dimensions which define its geometry. The width, thickness, and length of a resistor. So I could view it as a passive, as a resistor. So if you look at that, the resistor is from a, we call the macroscopic view. We know that Ohm's law tells us that current equals to V over R, or the resistance is defined by, or this is the voltage across, and this is the current that's been going through, right? Or R equals to V. The voltage across this resistor is divided by the current, right? Is there a problem? Good. And we talked about how does, if I want to look at there's the resistivity of the material. So the material has a resistivity of rho as its resistivity. It's called the Okay. So we know that a linkage between resistance in this block of material, we know that R, I think I talked about that a little bit, but I would just like to review it a little bit. So for R equals to rho proportional to length inverse with cross-sectional area. And the cross-sectional area here is T times W. Oh, right? And we know that if you have a thin film resistor in thin film, and this happens in most of the integrated circuits, in thin film resistors, T is typically fixed by technology. So whatever technology or layers you use, you're going to have a fixed thickness. So once T is fixed, I'm just going to take out something that I cannot control, which is the material itself and the thickness of the film. This is controlled by the film. Once you build the film, once we layer the film, there's no way you can change that. So to control resistance, we simply by controlling the width, W and L, right? So this is typically referred to as, if I'm looking at the top view of this, it will look something like this, right? So if I'm making a resistor in a planar process, meaning that I can only define the length and the width. So I can cut them into squares. Okay, so 6 squares. So if I'm making a connection here, this is my wire. So if I'm making a resistor, then this will be 6 squares. Okay? And then the resistance is, once again, the resistance is equals to this. This is called the shear resistance times number of squares. So if you're making, if you design a resistor through integrated circuit, thin-film resistors, typically people will tell you that the shear resistance, for example, it's called the shear resistance of the film combining is essentially resistivity divided by thickness. So it will probably be, let's say, 10 ohms per square. So if I'm drawing a 6 square, it should be, your resistor should be 6 times R. That's 60 ohm. Okay? So you should be able to estimate the amount of resistance you can build out of this shear resistance. And the reason why you see most of the resistance being built in integrated circuits are like snail glide, they route like a snail, is because we want to increase the number of squares. Because most of them has relatively low shear resistance, most films. Okay? So this is one of the parts that I want to review a little bit, and then we're going to look at, this is the microscopic view of a resistors. But if I only want to look at current density, relationship of current density and resistivity, then I probably can do it in here. Let me use a different color. Let me use this block. So what if I wanted to do it in a microscopic view, meaning that I'm looking at current, not the net total current. I just want to look at microscopically looking at current density. So if you look at J, which is current density, that's essentially equals to, by definition, is current divided by cross-section. And we know that J equals to 1 over V over R, right? And then I'm going to insert the R into A. The resistance equals to, sorry, I made a mistake. Length divided by this voltage, sorry. Okay? So if you look at this equation, I have a common component, which is area. Therefore, my J can be simplified into times V over L. So if I'm applying a voltage across this structure, so this is the voltage at this terminal from here to here. The voltage is V. So what is V over L? Does anyone know? Correct, electric field. So then this, we typically refer this to as, the inverse of resistivity is called conductivity times electric field. And typically there's a direction because current move in the same direction in electric field, so that we get J equals, so this is the microscopic Ohm's law. You look at Ohm's law as proportional to conductivity and electric field. Okay? So what we're going to do next in discussing semiconductor devices is that we need to understand how does one control conductivity in the material. So if you, before we start, you can think about what determines conductivity. If you look at if it's a bunch of carrier moving, then it would depend on, what depends conductivity? What do you think? What are the key factors that depends conductivity? We're going to, of course, do derivation in the follow-up analysis, but one of the key understanding is to things controlling conductivity are basically two factors. One, I should say, carrier density. The amount of carriers, charge carriers, I should say charge carriers. So in semiconductors, there's the electrons. I'm going to introduce the concept of holes. So these are level carriers. So how does one control the amount of electrons and holes inside a semiconductor, which will, of course, govern the conductivity of carrier? Because if there's a lot of carriers, then we'll make our flow as increase as high as possible. So it depends strongly on carrier density. And then there's also so then we need to know how fast can they move, or how do they move. So the movement's called, we're going to talk about something called carrier transport. How do they transport? It's like estimating the flow of people. It depends on how many people are actually present in a particular room, and then how fast they come in and go out. So the turnaround time of the system will depend on carrier transport mechanisms. Okay? Good? Any questions? So as I said, our introduction part is probably way over, so we're going to, for the next hour, before we actually start the next hour, let me just briefly go through what we're going to talk about. Today. So as I said, there's two key topics in chapter 2. So we're going to start chapter 2 now. There's semiconductor physics is a course you can take like maybe 1 or 2 semesters. It's, if you want to go deep, it's very deep. We're just going to spend an hour or so just to give you a sense as to semiconductor, the rudimentary of semiconductor physics, very, very basic. And then once we introduce how does one control carrier, type of carrier concentration in carrier transport, we're going to talk about one of the key elements in creating nonlinear behavior in p-n junction in semiconductor structures, which is called the p-n junction. So these are the two topics we're going to talk about. For semiconductor physics bar, we're going to talk about, first of all, what is the unique feature of semiconductor. Why is it mostly in the fourth group of elements, built with fourth group of elements, and why does one use silicon in most integrated circuits? But nowadays, people also look at getting third generation semiconductors, something like for different purposes. But we're not going to touch on that. We're just going to spend mostly on group 4 semiconductors. And then we're going to talk about, as I said here, what are the key components that control current and voltage relationship of a material or I should say, a microscopic view, the current density and electric field relationship in a semiconductor, what depends on carriers. So we're going to talk about what type of carriers in silicon. There's different type of material. We're going to introduce something called the intrinsic silicon. Is as pure. When you purify it, you get the intrinsic silicon in crystal. And then there's dopings. You can add dopings. So there's intrinsic and extrinsic, I should say. Extrinsic, meaning that there's N-type and P-type. And the type is controlled by doping of introduce impurities. And there are of course, impurities, different type of impurities. We're going to talk about that and how does it form N-type and P-type semiconductors. And then we're going to talk about, once you have the structure, how do you control or analyze its carriers. Once I do this, the carriers, the free carriers, as I said, there's electrons and there's holes. And its density typically referred to as N and P in numbers per centimeter square. So how do you find out the amount of electrons and holes in a particular semiconductors and its density, and then how does through doping, how does one control its carrier type of carrier and carrier concentration? Okay, so that's what we're going to do when we come back in 10 minutes. I hope I'm not.
喂，完全没有。喂，一点点。
刚在哪里回我？
喂，真的有这么小吗？一点点。喂，哦有。
差不多这样子。等一下要再调。
I'm just aligned with the. Go ahead and start. Hello. Hello. We're going to start resume our discussion, but before that, I want to just lay out some rules. I think in previous semester, because of the COVID situation, we have live streaming and also recording provided for all the students. Nowadays, I would like to encourage you to come to class. I think that's probably the best way to learn, and we're going to have some interaction. So the plan is then, we can take on. It's okay. Just not deal. The plan is then we're gonna, if you get sick or you have to have legitimate reason for asking for a leave of absence, and if that, you can send an email, then we can send you the live link of our streaming video. But we still have recordings available in the system, but if you want live stream, you have to send email and ask for a leave of absence, and then we can send you the live link. Otherwise, just come to class, okay? That's just. So regarding the discussion in the last hour, is there any questions? So if you have any questions or feedbacks, you're welcome to express it. For example, am I moving too fast, or am I talking too fast, or anything, okay? Any questions? Hello? Any questions? Okay. So if not, we're going to answer the question that we actually discussed before, which is, why do we look for materials especially in the fourth group? So why? So I'm going to simplify by why we're using silicon for now. So if you look at the periodic table, you just highlighted in the first group the elements are, I'm just going to get the periodic table. So someone help me fill the components. That's actually being used commonly in semiconductor devices. So it's the group fourth and its neighbor 5 and 3. So if you put in silicon, this is silicon. Let me highlight. Anyone come to fill it for me? Oh, you got all the stickers now. Okay. I want to fill okay. Yes. Good in chemistry. Oh, that's good. We get 5 stickers or something. Do we have stickers? Yeah. Okay, you can go and get stickers. Okay, so we started with identifying which one. So this is silicon, this fourth group. So what is the typical characteristic of a fourth group material? First of all, let's so if I'm doing carbon, this fourth group, right? So you start with 1s, 2sp. Carbon has an atomic number of 6, right? So it has 6 electrons. So the electrons, let me highlight it here. One is how many? How many electrons? The chemistry guy. 2, correct. 2sp. Anyone know what sp means? Correct. You're good. So 2sp, how many? It's 6, right? 14, 32. 2sp, how many more left? 4. There's sp, there's 4, we call them valence electrons. So, sticker time. Who wants to come and fill that for me? Anyone else have? Yeah. 14. Do the 14. We can also do germanium. You want to do germanium? Just do the same. And label the electrons. How many electrons in each layers? Only 14. Correct. It's okay. This is good. No, there's D. How many? And the external will be correct. Good. Yay. Okay, so once we know that in the fourth group, I'm not going to care what's inside, but at the external, because it has 4 electrons, so electrons, the sp orbital will actually combine, because when it actually in a crystal form, this is the sp orbital only happens in a crystal. If your materials is in crystal form, which it forms something called a covalence band, silicon. So if you look at a silicon crystal, what happens is that you have silicon. It has 4 electrons. So it hands out 4 hands in a we call it sp orbital. If you actually want to look at what the sp orbital is, just go get a 粽子, 有没有? 粽子 is the 4 angles of 粽子. So it's the connection to other orbital. If you want to look at it in a 3D fashion, it's like the tip of the angle direction is tip of the 粽子的那个方向. So then, what happened is that this silicon has 4 covalence bonds, and it's combined. In the crystal, it has a lot of silicons. So the other silicon, the silicon on the left or right, let me use this. It has its 4 valence electrons. So it will then combine with this silicon to form 8. So I have adjacent silicons. Therefore, this silicon will then see the sharing of electrons. So it sees 8 electrons. So it's a very content mode, because we'll see the sharing of the overall 8 electrons in the outer shell. So it has its 4 electrons, but coming with the other bounding, this band is called. The other electron is coming from the share, so from the adjacent, so this is called, the bounding is called a covalent. I should say, bound, adjective. So once you form a covalent bond, it's actually a very stable crystal. We know that for carbon, if it's in crystal form, what is it? What is forever? Diamond is forever, yes, diamond. So carbon is actually in crystal form with 4 covalence bonds. It's very strong. It's diamond, right? So then silicon is less because it's slightly larger, so that its electron force is not that good. So you can expect that it has a weaker, so this has the strongest covalence bond. So if I want to compare the strength of the covalent bond. Of course, carbon is forever, right? Silicon and then germanium. Because germanium is actually at the outer shell, so it has less control. It's not that strong. But you can assume that it's relatively stable. These crystals are in its relatively stable condition. Okay? So let's say I have a piece of intrinsic silicon. Intrinsic simply means that it's pure. Intrinsic silicon in its crystal form. Most of our substrates in the silicon substrates or silicon wafer substrates. Silicon substrate wafers are silicon crystals, crystalline silicon, I should say crystalline. Or crystalline silicons. So they form nice covalence bond. Of course, there's different silicons, there's different form. One is called a polycrystalline silicon, the other is called amorphous silicon, meaning that it's not in crystal form. Amorphous silicons are very commonly seen in panel. So panels are, or solar panels, or display panels, they use the silicon coated in glass, so that's amorphous or polycrystalline. But in silicon substrates, the IC you see, or the silicon wafer you see as a dinner plate size, those are made with, those consist of crystalline silicon, meaning that it has very, very strong covalence bonds. So first of all, the question is that we have, first of all, we already established for silicon, it has relatively strong covalent bonds, meaning that I don't actually have, so where there's free carriers. So there's no free carriers because each of them are occupied in the covalence bond. There's no free carrier. Where does free carriers come from? Comes from? So this is a situation where it's like now in the class, all of the seats are occupied. So everyone are content. They have a seat, there's no problem. Everyone is sitting in their seats, and we assume that we have a fully packed room. That's when you have intrinsic silicon, where with everyone seated in their seats, okay? But then, if there's agitations, for example, if the room got very hot, or there's people hanging on money, I don't know. If there's a disturbance in the system, meaning that if I have carriers who can acquire energy, there's always energy in the system. Of course, one of the simple ways of acquiring energy for these carriers are thermal agitation. So if I'm putting this material in a 0 Kelvin system, there's actually no energy in the system. But if I'm raising these materials in the putting this silicon substrates into a higher temperature, or raised to just room temperature, there will be thermal excitation once the temperature is not 0 K. So there's thermal agitation, there's a possibility of someone standing up, even though most of them are sitting down, but someone gets extra energy from the system through thermal vibration, and thermal excitation, it will break bounds. So if you look at this, if I have a silicon crystal, once again, like that, like this. So there's electrons standing up, and then it becomes it becomes a free carrier. So if it leaves the covalence band, it will then become free carriers. And then once it stands up, let's assume it's a packed room, right? So if it's a packed room, once the electron left, what happens is then there will be a seat. There will be empty seat. So this covalence band only have one electron. It will like to have someone to sit down. So there's empty seat is typically referred to as a hole. Then you will see a hole in the room. So like I said, if you think about the room, it's a packed room. If someone's standing up, it will leave an empty seat. That seat is called a hole. Both of them are free carriers. The way to think about holes are electron. We know that this person standing up, we can move around. If there's electric field, it will then conduct current. But how does hole conduct current? How do you think about a hole? How do you see a seat moving? It's if I'm handing out, I don't know, candies in front. So if this person stands up, the next person will like to sit in this seat. So you will see the empty seats actually moving to the back. So that's how you see hole moving. That is why the holes are also referred as a free carrier. It's the moving of empty seats in the system, because the next electron might come over. So this electron might come down. Actually, I'm using green. And then you'll see the hole shifted to the back. Okay? So both of them can be viewed as carriers in the system. So that's very important. You break balance and you generate okay? So these things happen in a pair. It's very important. In intrinsic silicon, what happened is that because think about it, you saw with the packed room. So anyone stand up accounts for empty seat. Even though the seat can move around, it can move to the back. The person the standing up electron still in front. It doesn't really matter. The amount of empty seats should equal the amount of holes. So it always come in a pair. Okay? This is very important. Will be in quizzes and exams. So this is a very important concept. In intrinsic silicon, seats always equals to electrons always equal number of electrons always equals number of holes, because you saw with the packed room. Okay? Good? Okay. So then how much does it take to break the bound? Typically it's referred to as the energy required to break a covalent is typically referred to as the minimum energy, I should say the minimum. Minimum energy requires to break the bound is typically referred to as EG, which is, if you view this device in an energy band diagram, that's something, if you're interested, you should go take courses like solid-state devices. But then the typical things that's referred to in material is called the energy band gap. This is called the band gap. Band gap of a material. Does anyone know how much it is for silicon? Any thoughts? This energy is typically in the order of electron volts. So it's one electron moving 1 volt. The energy required for an electron to move 1 volt. That's called EV. In EV. In numbers? How many? Yes, correct. You guys are good. So for typical semiconductors, you have, of course, these are, this is the band gap for the most popular material in semiconductor, but we would expect that it would be depending on the covalent bond. So we know that silicon, the band gap of silicon should be larger than that for germanium. Germanium is about 0.6. And then, of course, carbon is a lot, it's not really a semiconductor, it's considered an insulator. But the materials such as gallium nitride, this next generation semiconductor, may be up to 3 volt. So for semiconductor, you will see EG ranging from maybe 0.5 to all the way to close to 3 volt. This is like something like gallium nitride for blue light operation. Okay, so the basic, so you get a sense as to what this energy band, energy band gap means. It means that the energy requires to break the bond to generate electrons and hole pairs. So then, the next thing we want to know is then how do you determine the amount of carriers in intrinsic silicon? It, of course, would depend on 2 things. One is this, right? So there's 2 parameters. You will expect something called, we define something called the intrinsic carrier concentration in a silicon. Is referred to as Ni is equals to N equals to P for N intrinsic carriers. We know that, let me highlight it. So N is electron density. Once again, electron density should equals to hole density because someone sends out is going to leave a seat. So it's all in the unit of number per centimeter square. Okay? Good? So first of all, in intrinsic semiconductor, N always equals to P, and this number is called intrinsic carrier concentration, Ni. And if you take courses in solid-state devices, we'll go through the derivation to determine how do you determine Ni. But in this case, we're just going to give you the expression. So as I said, Ni will depend on 2 things we talked about. First of all, the energy required to break the bond. The energy required for this person willing to stand up. If the band gap is low, then you expect more of them will stand up, right? If the band gap is high, it's harder for this person to stand up because it requires a lot more energy to leave the seat. So that energy, of course, will determine. The other is, of course, external force, external energy in the system, which will depend on temperature. So you will expect that it will depend on 2 things, Eg and temperature, which is T. Okay? So the 2 parameters that will determine your intrinsic carrier concentration, of course, is material, its energy band gap, and also the environment, which will excite the breaking of covalence bond. So Ni, I'm just going to write it down. There's, of course, some parameters, but 2 things. I only wish to highlight 2 things. One is 2 things. You don't need to remember the equation, but this is just to highlight the 2 dependent parameters. One is temperature. It has very strong temperature dependency. And we know that as temperature increases, you will expect that Ni would increase exponentially because it's okay. So it has very strong temperature dependency as well. And then, of course, the other, aside from other fixed constants, the other thing is it will depend on material, of course. So as Eg increases, Ni should decrease. This is also some exponential dependency as well. So this simply tells me that if we know that I have three materials, if I want to ask you at room temperature, for example, so at room temp, at the same temperature, Ni of germanium, Ni of silicon, or Ni of gallium nitride. Which one will be the highest? Which one? Make a pick. Any thoughts? We're leaving to this guy already have too many stickers. Any thoughts? Any thoughts here? No one's wearing pink. I see someone wearing pink in the back. No? Which one? Just pick one. How about, go. Yes? Silicon have the highest density? Why? Go back and see, look at that. If the temperature is the same, the inverse direction to the energy band gap. So which one has the lowest energy band gap? Yes, germanium, correct, you got it. So this one would then have the highest, I should say it goes like that. That would be the best. Okay? So the inverse to energy band gap. So this, meaning that the smaller the gap, meaning that it's easier to break the band, therefore there's free electrons and holes, okay? But you can go and just insert the numbers using 1.1 eV and then insert the temperature at room temperature, insert room temperature. And we know that you can find that Ni for silicon, this is for silicon, at 300 K, that's room temp, you then have Ni about 1.5 times 10 to the 10th. Okay? So what does this mean? If you see this number, you see, is it high or low? What is it? So the way to do this is to compare to what has actually happened in crystal. So silicon crystal, I should say silicon atom in crystal density. Atom density is how many in silicon crystal. So in the crystal, I think this is about 5 angstrom. So if we use that to do calculation, you can actually see the crystal density per centimeter, how many silicon crystal. So silicon crystal is about 5 times 10 to the 22. That is per centimeter square, I will have 5 times 10 to the 22 atoms in the same cube. So if you compare the two, is Ni over the crystal density. I'm just going to write down this. This is about, it's more than 10 to the 12 over 1. So what is it? This is 1 in a trillion? 1 in a million is 10 to the 6. 1 in a million is very rare already. Your 1 in a trillion is very, very rare. If you consider yourself an electron or a hole in an intrinsic silicon, the possibility of you meeting another holes or meeting another electron is very, very rare. So you run in a 10 to the 12th. So it's very low density. Basically what it means is that the carrier's density is very low, considering the condition. So both electrons, so in the intrinsic silicon, once again, N equals to P equals to Ni. It's considered very low density. Therefore, your resistivity is very high, or conductivity is very low for intrinsic semiconductor, intrinsic silicon. So first of all, we think about most of the, even though for germanium, I think it's probably in the order of 10 to the 12, 13 or so intrinsic level, is still considered very low inside the crystal. And so the problem is, first of all, most of the semiconductors, even though it's called semiconductors, if you do nothing, it's very similar to an insulator because it has high resistivity. And without doing modulations or doing alternation of its character, it will be very, very close to an insulator, especially something like gallium nitride is even worse because it would then have very high resistivity. And the next thing is, again, something that we don't like is that its carrier concentration depends strongly on temperature. And it's exponential dependency, meaning that if I'm operating my circuits, especially like today, it's very cold, and then tomorrow is very high in temperature, then there's large fluctuation in the characteristic of the material. That's something engineers don't like because it's sort of out of control. So how do we actually make it more controllable and operating in a desirable range, which we can, for the engineer, what you want is that you want to be able to control its resistivity. That would be the best. And then you want to make sure it's stable. So how does one do that? So we do something called doping or making it called intrinsic. So we're going to introduce something called extrinsic silicon. So that's why we need the neighbors. So what happened is that if you look at this intrinsic material, it's actually very good. It's very strong in strength. So it's actually a very good material in terms of mechanical strength because the material itself is very robust. But in terms of controlling its carrier, for intrinsic silicon, there's very little we can do. So then we wanted to do something called extrinsic silicon by adding, we call impurities. So you're no longer drinking, just water, pure water. You're adding salt or you're adding sugar. That's the same thing. So you're adding components into the water and then alter its characteristic. It tastes sweet or tastes salty. So we add impurities to change its characteristic. Not any impurities, but dopants. We call these impurities are called dopants from neighbors. So what we do is we add sugar or salt into the system. So what you do is you look for neighbors. We're going to explain why. So first of all, you want to introduce neighbor into the system, and then the reason why you want to have neighbors is because first of all, you have 4 covalence bonds. You look for something close. It's actually easier to embed into the system. So we could introduce 5-group material. These are called acceptors. So sorry, donors. I made a mistake. So for 5-group is donors, I'm going to explain why it's called donors. Is that you think about it, I saw with my silicon crystal. And I'm going to put in the neighbors with 5 valence band. I'm just going to put phosphorus. It's very close to silicon. I'm just going to put it in. And then it's going to substitute the silicon. So what it does is that we don't have a phosphorus atom substituting the silicon in a crystal, but it wouldn't have added electron. Because it has supposed to have 5 valence electrons. 4 of them are here, 1, 2, 3, 4. And then there's extra. So it creates an extra, introduce an extra electron. That is why it's called a donor, because it added extra electrons into the system. And then it would then create a free carrier without holes. So this is different from previous case. Previous case is that I have a full packed room, people stands up. Now I'm introducing extra electrons into the system without creating holes. Okay? So that's the structure of a donor type semiconductor, where because it has extra electrons, so it's typically also referred to as the N-type semiconductor. If I'm introducing, change the color. If I'm introducing a acceptor, which is the 4th group. So 4th group atom, acceptor. It's called the acceptors. And these are, for example, for silicon, again, I'm substituting 1 with the boron, because we know that boron only have international colors are right. Okay, so then there's a hole because it only has 3 valence electron. Boron only has 3 valence electron, therefore it creates a hole. So it will introduce a extra anti okay? So that's extra holes. Because of these extra holes, is typically referred to as the P-type. P-type silicon. You have the N-type by introducing donor, which coming from the group 5, or introducing acceptors from group 3. It's good? So typically, let me just give you some. So for dopants, there's 2 types. Let me summarize it. As I said, dopants are impurities that's especially picked, which looks closely, either it's from group 3 or group 5, one electron more or 1 electron less. These dopants are 2 types. One is donors. For silicon, its density is, we call it ND, is the dopant density. I should say donor density. How many of these impurities are introduced? Numbers per centimeter squared. So it's also in density. It's called ND. This is in group 5. And For silicon, you have a lot of choices. You have phosphorus, arsenic, and antimony. So you see in integrated circuit, there's phosphorus. Hey, let me use the right color. That's my blue. So you either use phosphorus, arsenic, or antimony. It's 10 SB. So if you go to the bottom, there's actually more larger atoms or heavier atoms. And the reason why, if you look at older generation of the integrated circuit, typically the N-type started with phosphorus. Nowadays, you see arsenic or even antimony, more heavier atoms. And the reason, of course, is mainly because in integrated circuit you want to place the atoms and wish them not move too fast. If it's a smaller atom, actually move under high temperature process. So therefore, you see as technology generation shifts, you actually move to heavier atoms. Okay, so that's donors and this will lead to N-type silicon. If you introduce them into the system, it will be N-type silicon. For acceptors, we have called the Na, and this is the acceptor, its density. It's also density, let me just leave that out. Density also in numbers per centimeter square. And it's group 3. It's from group 3, right? And the problem with with acceptors for silicon, you typically only see one, which is boron. Nowadays, people start to use something some start using indium, and this is very heavy. And the reason why these tools are not included is because, think about why. Why isn't we can use all of them? But here, we have been using boron for a very long time for P-type semiconductors, and these two are one of the key things of becoming an active dopant or a good dopant is that you have to make friends with silicon very well. So you have to bound, because the other three hands has to bound well with silicon. For things like aluminum, if you put aluminum to silicon, what happens is that they will segregate. They'll bound with each other. They will not bound with silicon. So that's just the characteristic of the material make it impossible to become a good donor. So to be a good dopant or donor or acceptor, you have to bound. Remember, the rest of your covalent bond has to bound well with silicon, but not all materials are like that. So there's only a particular type that bounds well and become, we call it active dopant, because you have to bound. If you're standing out on your own, it does not serve as a good dopant. Okay? So that's the main reason why you see limited selections for acceptors choices. Okay? So what happens is that once you dope, you then be able to introduce carriers without depending on thermal agitation. You don't need extra energy to break down. Then we already have extra electrons or extra holes. So this would then allow us to control the carrier concentration. So for N-type, first of all, you have to understand that your pure water does not taste anything, meaning that the amount of carrier is very low, 10 to the 10th. So if I'm adding arbitrary dopant, typically the doping, let's just give you a doping concentration. In most of the semicon concentration, 10 typically is higher than 10 to the 14th. So that's already 4 versus magnitude higher than impurity. So you're adding sugar is always tastes sweet. If you have pure water, just adding a little bit, then you see sugar. You get that sweet taste. So just to give you a sense, we refer to this as light doping. If it's somewhere between 10 to the 15th, 14th to the 16th, these are light doping. So if you look it up in notation, this can be referred to as, if I'm highlighting as N minus, it's a lightly doped region. It's called a lightly dope. Light doping. So for heavy doping, and somewhere higher than 10 to the 19th. That's typically referred to, if you look at in the illustration, you actually see plus, meaning that it's heavily doped. Anyhow, even with light doping or heavy doping, your doping level is always much, much higher than, even with this is still much, much higher than Ni. So meaning that I could overshadow the background light doping level. So the carrier concentration for N-type, we call the N-type. For N-type semiconductor silicon, I'm just going to use, we give a notation of N. The carrier concentration is approximately, I should say, ND, whatever extra you introduce, and plus its original. And because ND is always much, much larger than Ni, what happens is that this is typically approximated as the doping level would then introduce, each dopant will introduce an electron. The number of dopant is much, much higher than intrinsic carrier concentration, therefore it will dominate your carrier concentration. For P-type semiconductor, it will introduce holes. So we're going to give you a notation. So because this is the N-type, so we highlighted with an N. So in N-type semiconductor, electron concentration in N-type semiconductor is called Nn. So the same thing for P is that P-type, whole concentration in P-type is determined mostly by its acceptor concentration plus Ni as background P, background whole number, so that's approximately Na. Okay? So because in an N-type semiconductor, what happened is that the way to think about, I don't think I have time to talk about that, but let me just introduce this. So in N-type semiconductor, we have electrons in the density of N, holes in density of Pn. Pn meaning that the holes in extrinsic semiconductor. We're going to talk about that. So this is majority carrier. This is minority. So the amount of holes, we're going to discuss that. You will expect that it will be even less than its original background. We're going to talk about it later, but let me just define P. For P-type, its majority will be holes in P, so that's majority. And its minority is electron, and P is minority carrier. So before I let you go, you think about why Pn, NP, are typically much, much less than Ni. And why? So we're going to give you the answer next week. So you start with the background population, and then anyone has thoughts? Want to answer it now? It's like, I can give you an example. 因为它那种生态系有没有？就是说你如果放很多老鹰，然后那个虫子就变少了那种概念，有点像这样子。就是 it's the same thing when we combine. So then if I have more people coming in, there's a possibility of empty seats will become less, because if I introduce extra electrons to the system, it will spot any empty seats, even though it's rare. Once it sees the seats, will sit down. So that's the reason why there's a generation recommendation called the mass action law that will tell us the majority and minority carrier once we introduce these extra electrons or extra holes. Okay? Okay, we're going to talk about that. I think my time is up, so we're going to talk about that next week. Hopefully you can move faster.